In this video, I will look at a number of different storage solutions. These include basic solutions to more advanced enterprise solutions. By the end of this video, you will have a better understanding of what is available and how it can be used in your company. In this video, I first look at software versus hardware solutions. Next, I will look at JBOD, or just a bunch of disks, and spanning. Both of these solutions allow multiple hard disks to be combined together to form the one drive. Next, I will look at the more common RAID implementations used in the workplace. RAID allows the administrator to combine multiple hard disks together for performance or redundancy reasons. Lastly, I will look at storage solutions. Storage solutions allow the administrator to dynamically control how drives are allocated. In this case, I will have a quick look at Windows Storage Spaces and Logical Volume Manager for Linux. Both these systems are excellent storage space systems and allow multiple drives to be combined and space dynamically allocated as required. The first point to consider before choosing a software or hardware-based storage solution is if you will use hardware or software. A hardware solution will generally cost more than a software solution. Nowadays, a lot of motherboards come with RAID solutions at no extra cost. If you start looking towards having a RAID solution in a server with hot swappable drives, this can push the cost of the server up. For a server, purchasing a system with RAID and hot swap drives is recommended. Hardware has the advantage of taking some of the load off the system. Since some of the load is processed by the hardware, this generally makes hardware faster than a software-based solution. A hardware solution will have the operating system see multiple drives as one drive. For this reason, a hardware solution can be used to boot the operating system. In some cases, you may need to add additional device drivers to the operating system in order for the OS to see the drive. However, it should be possible. With a software-based solution, it may not be possible to boot the operating system depending on which configuration you choose. This is because the software must first be loaded in order to access the drive. In some operating systems, you are limited to what you can choose for the boot drive. It is a matter of checking the operating system and seeing what it supports for booting. The advantage of software is that it may offer additional features. As we will see, there are software storage solutions that have advantages over hardware-based solutions. However, enterprise-level storage solutions may have these features as well, but the cost of these features is considerably more than compared with the software. The first solution that I will look at is JBOD, or just a bunch of disks. This solution combines multiple drives together to form one logical drive. Unlike the other solutions that I will look at, the drives do not need to be the same size. The disadvantage of this system is that it offers no redundancy. It only takes one drive to fail, and all the data is lost. JBOD also offers no performance increase. The advantage of JBOD is that you can combine multiple drives together of different sizes, speed, and from different manufacturers, but does not provide redundancy or speed improvements. The next solution is called spanning. Typically a software solution, spanning allows the free space on multiple drives to be combined into one drive. Let's consider the following example. There are 3 hard disks with free space that is not being used. Spanning allows the free space from each of these drives to be combined into the one drive. This allows you to use some free space that may have otherwise gone to waste. However, doing so offers no performance improvements or redundancy. If any drive used in the span set is lost, all data is lost. The next group of solutions that I will look at is RAID, or Redundant Array of Independent Disks. These solutions combine multiple drives together to form one drive. The drives in the RAID, also known as RAID array, need to be the same size. If you attempt to use a larger drive, it will generally be allowed. However, the extra space on the drive will not be usable by the RAID. The drives in the RAID should also be of similar specifications and speeds. If you have a drive that is slower than the other drives, depending on which RAID you are using, This can slow down the whole RAID to the slowest drive. Depending on the features supported by the RAID, it may or may not support additional drives to be added to the RAID later on. This is the case with most RAIDs. In order to add additional drives to the RAID, all the data on the drives needs to be reorganized. The more expensive RAID solutions may have the ability to do this. The cheaper options, like RAID included on the motherboard, will not, meaning that the RAID will need to be destroyed and recreated if you want to expand the RAID later on by adding additional drives. I will now look at some of the more commonly used RAIDs on the market. The first RAID level that I will look at is RAID 0. RAID 0, also known as striping, is when two or more drives are combined together. Data is distributed across the drives in blocks. As you can see, when a file is written to a RAID 0 drive, it is divided up into two parts, and approximately half is stored on each drive. As both drives can work independently of each other, this improves read and write performance. Notice that as more files are added, they are automatically divided up between the required drives. In this example, there are two drives. However, this could be expanded to any number of drives. For example, if you had 5 drives using RAID 0, potentially all 5 drives could be working at once to read and write at the same time. You can see why RAID 0 performance for reading and writing is so good. The downside of RAID 0 is that it has no redundancy. If one drive was to fail, you would lose all your data. In this example, if the second drive was to fail, notice that the first drive only has approximately half the file information, so effectively, this drive is not that useful without the other one. Sometimes students have trouble remembering which RAID levels have which features. To remember RAID 0, I like to remember that RAID 0 offers 0 redundancy. The other RAID levels that I will look at do offer redundancy in some form. The next RAID level is 1. RAID 1 is also known as mirroring. RAID 1 requires 2 drives. As you can see, as files are written, an identical copy is stored on each drive, making 2 copies in total. Since both drives hold the same information, this effectively reduces the usable space by half. Even though this effectively doubles the cost of drive space, it offers redundancy. If the first drive was to fail, the same exact information is available on the second drive. It just becomes a simple matter of replacing the failed drive with another one and copying the data from the first drive. The disadvantage with RAID 1 is that there is no performance increase. Since both drives work together and have the same data on them, reads and writes are effectively the same as using the one drive. So RAID 1 essentially doubles the cost of your space and provides redundancy, but with no performance increase. The next RAID level is RAID 5, also known as striped with parity. This requires a minimum of 3 drives. One of these drives, however, is lost to what is referred to as parity. When data is written, notice that all 4 drives are required to write information. The last drive in this case contains parity information. Parity is additional information stored about the data. A simple example of calculating parity would be to add the data from the previous drives and store the result on the last drive. Generally, most RAID 5 implementations will have the parity information rotated through each of the drives rather than store the parity information on the one drive. Using this parity information, the RAID drive can still operate if one drive were to fail or perhaps was stolen. The drive can simply use the information on the other drives to work out what the data should be. If a second drive were to fail, all the data on the RAID would be lost. For this reason, you should always replace the failed drive on a RAID as soon as possible. Once the replacement drive is installed, it will use the information from the other drives to rebuild itself. RAID 5 has additional advantages other than redundancy. Notice that when a file is read, in this case, 3 of the drives are used at once to read the file. This means that read performance on RAID 5 is excellent. The more drives in RAID 5, the faster the read performance. Notice, however, what happens when a file is written to the drive. Notice that all 4 drives are used, including the parity drive. Since the parity also needs to be updated, in some cases the other drives may need to be read to find out what data exists on the drive. Essentially, this means that regardless of how little or how much data is being written, all RAID 5 drives need to be used. This makes RAID 5 very fast for reads, but very slow for writes. Since RAID 5 effectively only loses 1 drive for redundancy and offers performance increases for reading, it has been popular in business, but that popularity has reduced in recent years. The main problem with RAID 5 is, if a drive fails, it is possible to have a second fail before a new drive is installed and has had a chance to have the data copied onto it. With drives getting larger and larger, the rebuild time is also increasing, and it is not uncommon in business to have RAIDs with 10 or more drives in them. If a second failure was to occur during the rebuild, all the data in the RAID would be lost. So essentially, there are 2 issues that need to be addressed with RAID 5: the performance for writes and the ability to deal with multiple failures. To address these issues, RAID 1+0 was developed, sometimes referred to as RAID 10. RAID levels that combine 2 RAID levels together are referred to as nested RAID. The first RAID level is RAID 1. This works as you would expect RAID 1 to work. Data is mirrored across the drives in the RAID, offering redundancy but no performance increase. To offer a performance increase, a second RAID 1 array is added, which is striped with the first using RAID 0. You can see now that when data is written to the RAID, it is divided into 2. Half the data is written on the left and the other half on the right. This offers excellent read and write performance. Since the same copy of the data is held on 2 drives, the RAID can survive multiple failures. The downside of this is that the cost to implement effectively doubles. With the cost of storage decreasing, RAID 1+0 has become more popular in business. It is hard to tell how multiple failures are handled with only 4 drives, so let's have a look at a RAID 1+0 in a bigger implementation. In this implementation of RAID 1+0, there are 8 drives in total. Half the available space is lost due to redundancy, but as the data is spread across 4 drives, read and write performance is quite good. If a failure of one of the drives was to occur, there is a drive with the same data available to recover from. If a second drive was to fail, notice that there is a drive next to it with the same data as this drive, so the RAID is still recoverable. If a third drive was to fail, the RAID is still recoverable. The only time the RAID is not recoverable is when a situation like this occurs. Let's say a drive fails, and then the drive on the second RAID 1 array that contains the same data as the first drive also fails. In this case, 2 failures could cause all the data in the RAID to be lost. In this scenario, there are only 4 sets of mirrored drives. However, a typical business scenario may have a lot more drives in it. Imagine you had 20 drives with a total of 10 RAID 1 mirrors. If this were to occur, the chance of 2 drives holding the same data failing at the same time is quite low. You can see that RAID 1+0 offers redundancy, but none of the performance problems associated with RAID 5. There are also variations like RAID 0+1. The difference is that the drives are arranged using RAID 0, and then these drives are mirrored. Like RAID 1+0, this offers the redundancy and performance improvements. Just like before, it can still operate after multiple drive failures as long as 2 drives do not fail that have the same data on them. The downside with RAID and other solutions like these is they are generally not dynamic. That is, drives cannot be added and removed as required. If you use a storage system, this will allow drives to be added or removed as required. They generally do this by placing drives into a pool. If you, for example, had 4 drives in the one system of different types, you can see here there's a mixture of solid-state and hard disks. These drives could be combined into one storage pool. The storage pool effectively manages the drives and their free space in the pool for the administrator, giving the administrator the one pool of free space. The administrator is then free to create drives using the space in the storage pool. For example, they could create a drive that is mirrored for redundancy in case a drive failed. The administrator could also create a drive with parity for better performance, or a drive with no performance or redundancy requirements. If a drive in the system were to fail, the administrator would need to replace this drive just like in a RAID system. Once the drive had been replaced, the storage system reorganizes the data to ensure that the drive meets the required specifications. That is, the mirrored drive has at least 2 drives with the same information, and the parity drive is spread out amongst the available drives for better performance. You can see that the storage pool handles all this for the administrator. The administrator only needs to worry about replacing failed drives or installing larger or additional drives when more space is required. For this reason, storage pools are often used in large deployments, where available space is often needed to be transferred between different customers. There are a number of different storage systems available. Often in enterprise-level SAN, you will find features that allow storage pools to be created and managed. In the case of this video, I will look at 2 software-based storage solutions. The first software-based storage solution that I will look at is Windows Storage Spaces. This is a Microsoft storage system first introduced in Windows Server 2012 and Windows 8. It is aimed as a replacement for Logical Disk Manager. It allows the creation of drives inside the storage pool, including the ability to have redundancy. The redundancy is using mirroring or parity. Although mirroring traditionally uses 2 drives, if you are using Windows Server 2012 R2, Windows can use 3 drives to store the mirrored data on. In the case of parity, the storage pool requires 3 drives. If there are 7 or more disks in the storage pool, and you are running Windows Server 2012 R2, Windows can spread the parity out on the drives to ensure that the data can survive 2 drive failures. The next feature in Windows Storage Spaces is that it supports thin provisioning. If you have any experience with virtual machines, you have probably come across thin provisioning. Thin provisioning is when the drive only requires space that matches the size of the data. As more data is added to the drive becomes larger, meaning it can dynamically expand as needed. Windows Storage Spaces uses the new REFS file system. REFS is designed to be a replacement to NTFS and offers additional features over NTFS. At the time this video was created, a drive created in Windows Storage Spaces cannot be used to boot the operating system. This means Windows Storage Spaces can only be used for data at this time. If you want your system drive to have redundancy as well, you need to use a different solution like hardware RAID or software mirroring. The next solution that I will look at is the Logical Volume Manager, or LVM. This is a Linux-based solution. The LVM was developed before Windows Storage Spaces and has the same features. Logical Volume Manager allows for drives to be added or removed without any downtime. Drives can be created in the storage pool with or without redundancy. The choice is up to the administrator. Once a volume is created, it can be resized as required. Also, the operating system can be booted from an LVM. LVM does require the distribution to support it. However, most modern distributions do support LVM. If you are using Linux, it is worth the time looking into LVM. This video has looked at some of the solutions available for storage for your computers. In later videos, I will have a look at how to implement some of these storage solutions. I hope to see you in those videos, and thanks for watching.